I want to just take a minute and do a different derivation of the same model, which just gives it a slightly different flavor. And you will see both of these forms in the literature. Both of these forms are discussed in the textbook. And you should probably see both of them because it's instructive. Let's start again with the world's most ridiculous model, x prime equals bx. And you remember B, it's the per capita birth rate, and it's a constant. But now I want to ask, suppose the birth rate is not a constant. And we mentioned, back when we discussed this model, we mentioned that the idea that the birth rate is a number, is a constant number, is kind of ridiculous. The birth rate has nothing to do with available resources. The birth rate has nothing to do with your age. The birth rate has nothing to do with your sex. The birth rate has nothing to do with anything. It's a constant birth rate for all animals. So let's take a step back from that. And let's say the birth rate is not constant. Let's say, for example, that the birth rate is limited by resources. And if resources are limited, then the birth rate has to go down. How would we deal with that mathematically? Well, we're going to take that B and not keep it as a constant. We're going to multiply that B by a resource limitation factor. So how do we come up with the math to represent the resource limitation factor? Well, here's a concept that you will hear a lot, that you hear a lot in ecology, the concept of the carrying capacity. And the carrying capacity is the number of animals that the environment can support. We're going to call that K. So K is the carrying capacity, and its units are number of animals, the total number of animals that the environment can support. If that's true, then what is X over K? It's the number of animals there currently are divided by the maximum number of animals there possibly could be. And that is the fraction of the carrying capacity that we are currently using. It's currently occupied. It's a fraction of resources that are currently being used by the X number of animals. And notice, by the way, that if X equals K, then the fraction is 1. And the fraction of resources that we are using is all of them, or 1. So X over K is the fraction of resources that are being used. It follows that 1 minus X over K is the fraction of resources that are not currently being used. But if that's true, then 1 minus X over K, the fraction of resources not currently being used, is equal to the fraction of resources available. So the fraction of resources that are available is 1 minus X over K. There is our new modified per capita birth rate. It's going to be the old fixed per capita birth rate times the fraction of resources that are available, which is 1 minus X over K. So our new birth rate is B times 1 minus X over K, which means our new model is X prime equals new birth rate times X, but new birth rate is B times 1 minus X over K. And so that gives us X prime equals B times 1 minus X over K, quantity times x. Okay, multiply that out. And what do you get? You get x prime equals b times x times 1 minus x over k. This is the form of the logistic model you will frequently see. We will refer to this many times in the future in this class. B times x times 1 minus x over k is the equation for x prime, the change in x. And notice now that if we multiply that out, bx times 1 minus x over k, we get bx minus b over k x squared. So now we've transformed that back into the first formulation of the logistic model, which was bx minus cx squared, only now we have shown that the c parameter must include both the birth rate and the carrying capacity. And so now we can make a much stronger statement about the C parameter, is that it includes at least these 6 factors. And you see in the bottom, it has to include in addition the birth rate and the carrying capacity. So that's our model. Let's ask a question. What behavior follows from this model? Well, you can sort of begin to stare at it and get some idea. Remember that we have a growth term, a positive term, that is linear in x, bx, but we have a limitation term that goes as x squared. And that means that as x gets larger, x squared is going to get much larger. And it's going to get much larger than anything times x. So eventually, for large x, the minus sign, the term following the minus sign, is going to dominate. The term with the minus sign is going to dominate for large x. So we have growth for small x, crowding for large x. When we simulate this model, as you will learn to do pretty soon, you will see that that is the behavior that is predicted by that model. That you see the rise, the initial rise, which almost sort of looks like an exponential rise. This almost looks like x prime equals bx, because x squared is small. But as x gets larger, it begins to assert itself and limit the growth until it saturates at the carrying capacity of the model. So basically, what we have here is the green positive feedback dominates the early part of the growth, and the red negative feedback dominates the late part of the growth until it saturates.